When you're trying to figure out what a function looks like so you can graph it, there are a few pieces of information that are very helpful to figure out in order to visualize or graph a function. And one of those is figuring out the inflection points. And not only inflection points, but also the intervals of concavity, where your function is concave up versus concave down. So in this video, I wanted to show you an example which came from my weekly live stream last week, which I'm doing every Monday night at 5 Pacific, 8 Eastern, where I go over how to find inflection points and then how to use those in order to find the intervals of concavity of a function. So without further ado, let's go ahead and jump on into the example. We're going to find the inflection points and intervals of concavity of this function right here. So intervals of concavity and inflection points are extremely similar to finding critical numbers and intervals of increasing and decreasing, just like we did in the last problem. Except what you want to keep in mind is that inflection points and concavity, those have to do with the second derivative. The second derivative of a function is going to tell you about those things, where the first derivative tells you about the slope and the intervals of increasing and decreasing. So rather than worrying about our first derivative, of course, we are going to need to find our first derivative in order to get to the second derivative. But rather than doing everything with our first derivative, we're going to be working more with our second derivative. So the first step in really any of these types of problems that have to do with finding inflection points is going to be to find our second derivative. So to do that, again, we're going to need to use the product rule in this case. So what we can do is we can say f is going to be this x piece here. G is going to be the square root of x plus 3 piece here. But instead of writing it as the square root of x plus 3, what I'm going to suggest is writing it as x plus 3 to the 1/2 power, because raising anything to the 1/2 is the same as taking the square root of it. So this is equivalent to the square root of x plus 3. But the reason why we want to do that is when we're then finding its derivative, when we're finding this g prime here, it's going to be much easier because we can use the power rule. Power rule combined with the chain rule will tell us how to find this derivative. So chain rule says, and we need to do chain rule because we have this inside function here and then this outside function basically acting on that. So chain rule says that we're going to take the derivative of the outside, which is this 1/2 power piece, which we're going to be able to do using the power rule. So we'll bring the power down in front. Chain rule says to leave our inside function the same. And then we're going to lower our power by 1. So 1/2 minus 1 is minus 1/2. Because again, you'd have to do minus 2/2, which is negative 1/2. Okay, and then our f prime, we just need to find the derivative of x. The derivative of x is just 1. So now product rule says that we can cross multiply these. X times this here is going to give us x. Actually, let's go ahead and write this in a little bit neater format here. We'll say 1/2 times x times x plus 3 to the negative 1/2. And then 1 times x plus 3 to the 1/2 plus x plus 3 to the 1/2. 1 times it isn't going to change it, so we don't have to write that out. Then, like I said, we need to find the second derivative. So now we need to find the derivative of this here. The second derivative is always just going to be the derivative of the derivative. There's two different ways we could go about solving this. We could do kind of like what we did in the last problem, where we could factor out this x plus 3 to the negative 1/2, or we can kind of carry on taking the derivative of each of these pieces separately. I'm not really sure which one would be easier. They'd probably be pretty similar. So we'll go ahead and just do each one separately. So we'll create kind of a separate little problem over here. So first of all, to take the derivative of this term here is going to be very similar to what we did to find the derivative of this function. We're going to have to do product rule. So we'll go ahead and say f is going to be our 1/2 x piece. G is going to be this other piece here, the x plus 3 to the negative 1/2. Then we need to find f prime, which the derivative of 1/2 times x is just 1/2. The derivative of x plus 3 to the negative 1/2, we're going to be able to just do power rule and chain rule, just like we did here. So we bring the 1/2 down in front. I'm sorry, bring the negative 1/2 down in front. Leave the inside function the same. Lower our power by 1. So negative 1/2 minus 1 or minus 2 halves, would be negative 3 halves. So our new power is going to be negative 3 halves. And then by chain rule, we multiply this by the derivative of the inside. The derivative of x plus 3 is just 1, so we don't really have to worry about that. And then product rule says, again, we're going to cross multiply these. So 1/2 x times negative 1/2 x plus 3 to the negative 3 halves. Those 1/2 are going to form a negative 1/4. Then we have an x, and then x plus 3 to the negative 3 halves. Okay, and then we need to do this 1/2 times x plus 3 to the negative 1/2. Let me get rid of that there. It's a little confusing. All right, so then plus 1/2 times x plus 3 to the negative 1/2. All right, and then we still need to find the derivative of this piece here. So we haven't done that one yet. So to do that, x plus 3 to the 1/2. Well, we've already taken that derivative of that over here. That was a part of our previous derivative product rule piece. So we already know the derivative of x plus 3 to the 1/2 is 1/2 times x plus 3 to the negative 1/2. Okay, so now this is our second derivative. It's kind of complex, but we're going to be able to do something similar to what we did in the last one, where we kind of factor some stuff out. So again, to find inflection points, we did our first step, which is finding the second derivative. Now that we have our second derivative, since this is such a similar process to finding the critical numbers, where we took the derivative and set it to 0, same idea here. We're going to take our second derivative and set it to 0. So again, we have these three terms here. Again, we have a similar situation where it's easier to factor this out, because then we're going to be able to create three kind of smaller, simpler problems out of that. So to factor this out, what we want to do is see, what do these three terms have in common? Well, they both have a 1/2 that we can pull out, so we'll start there. And then they also both have, or all three of them have, this x plus 3 to the negative 1/2 power. So we can also factor that out. And then we want to think about what's going to be left. So if we pull out 1/2, we're still going to be left with a negative 1/2 to get us to negative 1/4. We still have this x here. And then keep in mind, this is x plus 3 to the negative 3 halves, where we pulled out x plus 3 to the negative 1/2. So again, what power would we need to make our x plus 3 raised to, so that the power of this plus our negative 1/2 power out here adds up to negative 3 halves? Well, it would just be negative 1. Okay, and then what are we going to be left with in this middle term here? So we pulled out 1/2 x plus 3 to the negative 1/2. That's exactly what this was. But you do want to be careful. This isn't just going to disappear. Whenever you're factoring out something like this and you factor out the entire term, it doesn't just disappear. You need to put a +1 as like a placeholder there, basically, so that when you, because if you imagine distributing this back in, we need this term to actually be there when we do that. Okay, and then again, we factored out a 1/2. Our 1/2 is going to be pulled out, and then we have, again, this x plus 3 to the negative 1/2. So that could have kind of been simplified by just combining these two terms into the same thing. Either way, we're going to end up with the same thing there. It's going to end up simplifying down the same. Because what we can do is, instead of saying +1 + 1, that is just going to become +2. So now when we're trying to set this whole thing equal to 0, kind of like we did last time, what we can do is create these kind of two simpler problems. So we'll just take each of these factors and set each of them separately equal to 0 and solve those. So we will get 1/2 times x plus 3 to the negative 1/2 equals 0, and negative 1/2 x times x plus 3 to the negative 1 plus 2 equals 0. So this over here, if we multiply both sides by 2, that'll cancel there. 2 times 0 is still 0. So that's not really going to contribute anything there. Then to get rid of the negative 1/2 power, what we can do is raise both sides of our equation to the negative 2 power. Negative 1/2 raised up to the negative 2 is going to cancel out. So we're just going to have x plus 3 equals 0. Subtracting 3 over gives us x equals 3, minus 3. There we go. And then over here, we're going to minus 2 to the other side. So negative 1/2 x times x plus 3 to the negative 1 equals minus 2. Multiplying both sides by minus 2 to cancel that there gives us x times x minus 3 to the negative 1 equals 4. So this looks a little weird, but what we can do here is, instead of thinking of x plus 3 to the negative 1, think of it as x times 1 over x plus 3. Because anything to the negative power like this, you can get rid of the negative power by moving that whole thing down to the denominator like this. Okay, so since it's x plus 3 to the negative 1, that'd be the same as 1 over x plus 3 to the 1. Well, x plus 3 to the 1 is just x plus 3. So we can rewrite it like that. And now to simplify this, we can multiply this, as, think of it as multiplying fractions. You just multiply straight across. So what that's just going to end up with is x times 1, which is x, over 1 times x plus 3, which is just going to simplify us down to x over x plus 3. And that's equal to 4. Then we can multiply the x plus 3 over. So do be careful to put that in parentheses so that it'll cancel with that whole denominator, giving us x equals 4 times x plus 3, which then we can distribute that, giving us 4x plus 12 equals x minus x from both sides. 0 equals 3x plus 12 minus the 12. Divide by 3, giving us negative 4 equals x. Okay, so we got 2 inflection points here, but we do need to be very careful of something here. Notice our 2 inflection points are x equals negative 3 and x equals negative 4. But there's a problem with both of those numbers. Because if we go all the way back up to our original function here, our original function is a of x equals x times the square root of x plus 3. Think about what is going to, or basically what's going on with this function. Think about the domain of this function, I should say. You want to keep in mind that whenever you have a function with an even root, in this case we have a square root, you want to be careful that you cannot take the square root of a negative number. So basically what that means is any x value that makes what's inside the square root here negative is not a part of the domain. We can't actually plug that in. So when we're looking at this function, we need to remember that basically x plus 3, what's in the square root there, has to be greater than or equal to 0. So basically x has to be greater than or equal to negative 3, which means this first inflection point we got of x equals negative 3, it's not really an inflection point in the sense that this is a spot where our function is going to switch from being concave down to concave up, or vice versa, because it's really just the edge of the function's domain. Our function is not even defined for x equals negative 4, so that definitely is not a valid inflection point, because it's not even in the domain of the function. So you want to be careful when you find the inflection points to throw out anything you get that's not within the function's domain. Since this is basically right on the edge of the function's domain, any x values less than negative 3 are not defined. They do not exist in terms of this function. This isn't really like a point that we want to think about putting on our number line and figuring out anything to the left and right. I mean, we can, but basically all that does is it tells us that everything to the left of x equals negative 3, it doesn't even exist. And since we figured out that this is the only place where our second derivative equals 0, we know that there's not going to be any other place to the right of negative 3 when we're doing our test to figure out where our function switches from concave up to concave down. There's not any points where x is greater than negative 3 where it's going to switch, because there's not any other points where our second derivative equals 0. So what that tells us is our entire function basically is going to be either concave up or concave down. Well, to figure that out, we could just do kind of the same kind of thing we did with our first derivative test, where we were trying to figure out where it's increasing and decreasing. we could just take any x value that's within this interval of -3 to infinity. So let's just say 0, and plug that into our second derivative. I'm sorry, not into our function, but into our second derivative. And if we plugged x equals 0 into this function here, what you would find is that that would give you a positive number, which means that our entire function is concave up. So it's curving up like that. It's like a smiley face kind of. So basically our entire function is going to be concave up all the way through. Well, I hope you found that video helpful. If you did, please be sure to hit that like button down below, and be sure to join us on our weekly live stream next Monday night at 5 Pacific, 8 Eastern, where you can see me do more problems like this and interact live and hopefully get some of your questions answered too. Thanks, and see you there.